like to introduce you to Dr. Kevin Hagedorn to tell us more about life magnetics.
Hey folks, so I'm Dr. Kevin Hagedorn and our company is Life Magnetics. So stabilizing RNA is a significant problem for a number of emerging medical technologies. One example that you all are probably familiar with is the COVID-19 vaccine. As soon as the COVID-19 vaccine came out, what was the first news story that you heard? It was that we didn't have the infrastructure to transport and store it, right? The fundamental issue with RNA technologies is that RNA itself is extremely fragile. And that's become a major barrier to deploying new technologies. COVID was an exception because with COVID, you needed to get something that was safe and effective out quickly. It didn't matter that the distribution was a nightmare. But many other RNA therapeutics are not developed because the distribution doesn't justify developing the drug. Another example of an emerging technology where this is an issue is cancer vaccines, which are similar to the COVID-19 vaccine, but rather than training the immune system to recognize COVID, it trains it to recognize your cancer cells and kill them. It's actually the fastest growing type of cancer care. But in that situation, you have to tailor the vaccine to the individual, which then just amplifies the problems that you have. For example, at the RNA symposium at the University of Michigan last year, U of M, Cleveland Clinic, and Houston Methodist were all setting up sites to manufacture mRNA on site. And the reason that they were doing this is because manufacturing it on site is easier than ordering it from elsewhere because there's less logistics. That's how much of a nightmare the logistics are. They would rather make it in-house. So to solve this issue, in collaboration with Argonne National Labs, we did simulations to predict the structure of a carbon, which I'm not going to go into because it's a bit complicated, but we basically developed a way to modify the wave function above a carbon semiconductor in order to help stabilize RNA. And how this works then is we load the RNA onto the surface of this carbon, add a lipid. It stays on there when there's high calcium, and inside of cells there's a 10,000-fold reduction in calcium concentration. So inside of cells the RNA comes off and gets translated. We're doing this in collaboration with the University of Michigan to develop a better way to make stem cells. So stem cells are also important for regenerative medicine. For example, in this past year, people have used pluripotent stem cells to have example cases where they've cured actually sickle cell anemia and type 1 diabetes by taking a patient's cells, converting them to stem cells, making a gene edit, differentiating them, and then reimplanting them in the body. One of the key limiters there is the ability to convert them, because it's like trying to fill a bucket to a certain level when there's a hole in the bottom of the bucket. If you have too much RNA, it's toxic to the cell. If you don't have enough, the cell won't convert to a stem cell. So it's like the water's draining out the bottom and you're trying to fill it to the right level. You either have to put in a lot of effort in order to keep it stable at the point where you won't get the conversion. That's part of the reason why this is so difficult. But we've shown that we can have much longer expression times than the typical materials, which helps stabilize that expression to create these stem cells. But that's all really difficult, so we've got a quick, easier way to make money, which to do the conversion and transfection, you have to bind the RNA, get it into the cell, get the cell to release it, and then translate your RNA into proteins. The first two steps of that are just grabbing RNA and pulling it out, which we've been able to demonstrate in a decent application in milk testing. So cows get sick, there's zoonotic transfer of pathogens to humans. We can detect that in samples more effectively than other extraction kits. So we're targeting $1 million in revenue through a testing conglomerate in Lansing this year. And we're raising $300,000 to do so.